So here's my MEI FP2 syllabus on a page, and it's linked to the questions that are likely to come up from the students. 5 main topics, and I'm going to go around anti-clockwise, starting at Maclaurin. That's very suitable given we're looking at complex numbers where angles are anti-clockwise. So here we go then. Maclaurin, well, they're going to ask you to find a series solution, maybe the first n terms. They quite like log of 1 plus x, or arc cosh, or arc sin, or arc tanh. For the arc cosh, arc sin, arc tanh, that's quite interesting. As we differentiate the first time, we can get an expression which we can, it's just going to be a 1 over, say, x squared minus 1 or something, which we can then do a binomial expansion of, and we can look at the range of validity. Polars is our next topic. May well ask you to sketch one where you can create a table of values and points, or and get it to sketch in your calculator. Remember to put the salient point, the coordinates of the salient points, onto your diagram. They might ask you to convert to Cartesians if they've got something like an ellipse that you're looking at using your trig identities. They're pretty well certain to ask you to find a maximum or minimum point, so dr by d theta equals 0, and to find an area under the curve. So remember our formula, the integral of a half r squared d theta. And both of those are like to be in a single question. Next one, big chunky section, will be on complex numbers. The whole principle of FP2 is we're working in a polar form of complex numbers, r to the ej theta, or cos theta, cos theta j sine theta, that sort of concept. And so when we multiply the complex numbers together, we multiply the moduli, and then we effectively add the angles. If we're multiplying, so theta 1 plus theta 2, and if we're dividing, we're doing theta 1 minus theta 2, which means in effect, if I take a z, any z on my graph, and I multiply it by r e to the j theta, I'm effectively transforming it with an r is going to be a scale factor, and the theta is going to be a rotation angle. That takes us into the form that we're going to use for de Moivre, which says that cos n theta plus j sine n theta is equal to the cos theta j sine theta to the power n, where we're really looking at this idea that all complex, our base complex number is z cos theta plus j sine theta, and it's really useful to write that in the form e to the j theta so we can do a lot of solutions. So using the above, we can find cos 5 theta, because that's just a real part of a binomial expansion of cos theta plus j sine theta to the 5. And therefore we can get cos 5 theta in terms of cos theta to the power 5 plus cos theta to the power 3 plus cos theta, sort of with coefficients. Our second identity here that they use a lot is the cos n theta is therefore going to be z to the n minus z to the minus n over 2, and ditto similar for sine theta. Therefore we can find cos theta to the power 5 by taking that identity and powering up to the 5, doing a binomial expansion, and rearranging the terms to bring together z to the 5 with the minus z to the minus 5, and therefore we can find cos theta to the power 5 in terms of cos 5 theta with a coefficient cos 3 theta approach. And then we got series off the back, and they might give us a big C equals cos theta plus cos 2 theta plus cos 3 theta all the way up to cos n theta. And if we add the complex part js that matches, so j sine theta, j sine 2 theta, etc., we can see we've got a series, a geometric series in e to the j theta, or some variant of it, and therefore we can find the sum of that, the C, as being the real part of the sum from our formula. So that brings us through that. Roots of unity, or a complex number, z to the n equals 1 is our base option here, and of course 1 is e to the 2 pi j theta by any multiple, so k, an integer, positive integer, and therefore when we root that we can come down, can't we, and we're going to get some sort of factor of k over n. So we're going to get our regular polygons. So if we were looking at the cube, a root, we're going to get an equilateral triangle, then we're going to get a square, a pentagon, a hexagon, etc. And if we started with sort of complex number z0, then we also have to put that in, find the root of that, and of course that has the effect of scaling and rotating our regular polygons. Sometimes they then take our solution stat and they square it up, so it turns the hexagon back into an equilateral. So have a think about that. Okay, hyperbolic functions, well, we know cosh and sinh. We know their differentials and their curves. They may well ask you to prove the identities cosh squared minus sinh squared equals 1, or arc cosh x equals log of x, x squared minus 1. They may well ask you to look at using or proving the differential of arc cosh. They like these inverse functions. So what's the differential of arc cosh, arc sine, or arc tangent? Remember, we do that by flipping it over, don't we? Finding the inverse. So therefore x equals cosh of y, etc. And then using them in reverse by looking at the integrals of 1 over x squared minus a squared. So our solution is in arc cosh form. Very occasionally they ask you to do it by parts and do it the other way. So effectively you're going to differentiate your arc cosh to get back to that. So that's going to be your u in your parts. Generally they can put a solve an equation in. So you can either get a linear or a quadratic in a hyperbolic function, so cosh x equals 3, or you could get a quadratic in cosh x squared. The other way, occasionally to solve these, is to put them into break up the cosh and sinh into e to the x form and come up with a quadratic, which of course is exactly what we do to prove that arc cosh equals the log of, such as on the right there. Okay, and our final topic is matrices. And they're either going to give you a 2 by 2 or 3 by 3. We've got to be able to solve these equations first by finding the inverse matrix m minus 1. That means we've got to be able to find the determinant and work out what's going on when the determinant's 0, what's telling us about it, there are no solutions. They're going to ask us to find eigenvalues and eigenvectors. So these eigenvectors, yep, there are invariants. So we're going to use our formula. That then det m minus a lambda I is going to equal 0. That's going to give us our characteristic equation in lambda, which they'll ask us to use. They may well ask us to diagonalize a matrix, PD p minus 1 form. Remember, the D vector is our eigenvalues vector matrix rather, and the P matrix is our eigenvectors matrix. Make sure you get them in the right order, in a consistent order. So if you've got V1 is your first vector in your P, then lambda 1 should be your first eigenvalue in your D matrix. And of course from that they may ask us about finding m to the n, or the limit of m to the n, and n tends to infinity. And that's going to be our d to the power n p minus 1. They're going to ask us to go through Cayley-Hamilton and matrix that each matrix satisfies its own characteristic equation, and use that to find m4 or even m minus 1. So that's a fair chunk of stuff. In terms of more unusual questions which have come up recently, if we go look up to the left, they may well give us a matrix where we've got numbers in all of the in all of the columns and rows, except for somewhere in there they'll have a k value, a variable, and with that they'll be looking for where adjusting our k's, or looking for situations where there are no solutions, i.e. where the determinant is 0. And of course that's got a geometric link over, because if we've got 3 by 3, effectively we've got 3 planes horizontally in our looking across our matrix, isn't it? The first row, the second row, and the third row, they all represent planes. And then the geometric interpretation is whether those planes all intersect at one point, whether they might all intersect in a line, or whether they don't all intersect. So we get one of these sort of Toblerone effects where we've got 3 points and only 2 ever intersect. So that's the geometric interpretation. The other option they may give you is in our solution vector on the right hand side of the equation. They might put a variable p in or something there in one of those, and therefore we're going to get a family of solutions depending on the value of p, and they might ask you to interpret that as well. So there you go. If you like that, please tick the like button. Otherwise, very best of luck with the exam.